This is the second attempt at this question, so if I sound a little bit crossed, it's because I just lost my footage. Anyway, question 7. You are given a section of a polymer and the question asks for the structure of the monomers. Now this is not going to be a big deal in year 11 because you only learn one type of polymers, which is addition polymer. But actually what you always want to start with is to determine the type of polymer that you have. And an addition polymer is very distinctive, and it's going to look very different from a condensation polymer, which is what you're going to see next year. But an addition polymer will have a carbon backbone, just carbon, single covalently linked to other carbon. Very boring actually, if you think about, well, actually, we haven't seen it yet, but condensation polymer looks a little bit more exciting. But addition polymer only has a carbon backbone, and that's all that this section of a polymer has, so I know this is an addition polymer. Now, if you know that something is an addition polymer, however, that also implies that the monomer must have carbon-carbon double bond. So if I break the polymer, I will need to add carbon-carbon double bond back into between these carbon atoms. So the way that I tend to do it when the question asks for a monomer given the polymer, if I already know that it is an addition polymer, I will start breaking the polymer into its monomers, and you need to break it every 2 carbons because that will be where the double bond originally comes from. And this is a very simple example because the 2 monomers that I could make from this section, they are identical, so I know there's only one type of monomers present, and the only thing you need to do to get the monomer is to put the double bond back between the 2 carbon in the backbone. So you don't need to put any double bond here if we're wrong anyway. It has to be between these carbons, and if you do that, you will see that everything will now follow the octet rule. Fluorine will form 1 covalent bond and each carbon has 4, and that means that the answer is B. I mean, you should know straight away that A and D are wrong because you do need the CC double bond in the monomer anyway. So that's question 7. We are moving on to question 8, and I think what I'm going to do, I've just done something, and I'm going to save this before it crashes on itself the second time, which it probably will. That's a very good sign. Something is happening. What is not responding? Oh, okay, go back. Question 8. Which of these configurations describe the molecular geometry of PF3? Right, molecular geometry is the shape, not including the lone pairs of electrons. And in order to work out the shape, I'm going to start with valence structure. Even though the shape, the molecular geometry, doesn't count the lone pairs of electrons, you need to consider it because you need to take it into account when you consider valence, the repulsion of valence pair electrons. All right, P has 5 valence electrons. If you want to know how many valence electrons P has, try to find it on the periodic table. It is right below nitrogen, so in the same group, which means it has the same number of valence electrons, which is 5. And fluorine has 7 valence electrons. You can also find out this information by looking at the periodic table. Now what this means is that P is going to need 3 more bonds and F is going to need 1. So the actual valence structure for PF3 and valence structure does not require the actual shape. It will look like that. I think it's doing that thing again, which I still don't know why. I haven't really done anything to work out the reasoning behind this. I'm sure it's like a shorthand version or something. Okay, let's do that. Like, what is the purpose of disappearing after a while? Anyway, I've had enough. So the P will need to arrange the pairs of electrons around it in a way so that these 4 are as far apart from each other as possible. And the shape for that, if you want 4 pair of electrons, to be as far apart from each other as possible, then you need tetrahedral. And this takes into account both the lone pairs and the bonding pairs of electrons. So this is going to be the electron geometry. So I'm going to try to do tetrahedral. It doesn't look very nice unless you do it in 3D. But because the molecular geometry doesn't take into account the lone pairs of electrons, then if I just think about what the shape looks like, I'm going to do it in 3D. You don't need to do this in 3D in year 11. It's more of a year 12 kind of thing. So it looks kind of like a pyramid with the 3F being the base and the P as the top. So the shape is trigonal, pyramidal, which is C. Not entirely sure why I actually wrote that out. I can just circle the answer. Oh well, there you go. Question 9. Ooh, I like this. Alright. Consider the following reaction. I'm going to move the cursor down here just to be safe, because sometimes it does this weird thing. Oh, alright. You need to work out what Z is. Now, if you look at this is an alkene. And you know why? You know that it is an alkene because the double bond is actually shown very clearly, actually. And the alkene here is reacting with a halogen. So the product of a reaction of alkene is going to be the product of an addition reaction. Okay, I'm going to redraw this a little bit just to show the double bond a little bit more clearly. Actually, why did I do that? Hang on. Okay. CH3. So for the sake of the argument, I'm going to put the H down here. And then Br2 is Br, double single bond with Br. So when you have an addition reaction, what happens is that you are going to break one of these bonds, and it's going to do that thing again, does it? Yeah. Break one of these bonds, and why? Okay, now it works. And you're also going to break that bond. This doesn't, oh, I have no idea. And one of the Br is going to go and bond to this carbon. The other Br is going to go and bond to this carbon. So what you end up at the end, in terms of the product, is CH3, C. So I'm rewriting the whole thing. But now that you have broken one of the, why is there H there? Now that you have broken one of the double bond, you only have a single bond left, and you have the two bromine atoms now added to the molecule, hence the name addition reaction. Alright, so what does that look like in terms of the answer? Now obviously these answers are in semi-structural formulas or condensed formula. Alright, it looks like A looks good. It's not a very good way to write condensed formula. I would prefer if you put some brackets in, but it's not. It's okay. It is the only correct answer. I mean, this one randomly has an extra hydrogen. I don't know from where. This one also randomly has an extra hydrogen. Same can be said for that. I mean, B and C are identical, so none of them can be the right answer. That's question 9. All right, we're gonna roll here. We're gonna see whether we can do the next 5 questions without any accident. And I've come to realize that every time I save this document, it's gonna go not responding. But hopefully it's gonna go back and be normal. Yep. All right, we're good. Let's move on to 10. Compound. The compound that is a structural isomer to this. Yeah, all right. Okay. I may need more room than this. We'll see. No, I definitely need more room than this. Okay, that's good. We need to see structural isomers. Now, 2 things are structural isomers if they have the same molecular formula but different structure. So what you probably want to start is you want to work out what the molecular formula for this is. Now, this is propanoic acid. So you have 3 carbon, 6 hydrogen, and 2 oxygen. All right. So with any whatever that in here that has the same molecular formula is going to be a structural isomer of propanoic acid. So A, ethyl methanoate, is an ester. I'm going to draw it out, and hopefully you get better at this as you do more practice. So you have a C double bond O, and then you have a single bond. There's one hydrogen, one here, 1, 2, 3. I feel like my whole life's wasted drawing hydrogen. Anyway, it looks good. A is the answer. You know B is wrong because an alcohol only has one oxygen. You need two. Ethyl ethanoate. Now you get better at this with practice, as I just mentioned 2 seconds ago. But if you have ethyl ethanoate, that gives you a total of 4 carbon, so that can't do anyway. Propylmethanoate also give you 4 carbon in total, so that doesn't work. So A is the answer. And we are moving on to 11. Now, speaking from experience, I'm supposed to leave the cursor somewhere else, otherwise it does some like weird things. How many hydrogen atoms are there? And the cursor's back. How many hydrogen atoms are there in a molecule of 3-nonano? Now 3-nonano is the old name. That sounds so weird. Nonano. Now we call it non-trio. Not that it is any less weird. Kind of reminds you of like Italian something. I don't know what I'm doing. Ooh, that's bad. Okay. You don't have to do this if you think about it. I'm gonna do it anyway because when I teach people shortcut and they don't know how to use it, it actually is better to know how to use the long method. But anyway, I'm not gonna fill in any more hydrogens. Just gonna count because I can count in theory. 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, now what is the shortcut? What's the magic number here? The shortcut is to think about the general formula of an alkane. If you have C9, you're gonna have 20 hydrogens using CnH2n plus 2 as the formula. So if you think about, I'm gonna replace one of these hydrogen with an OH. So I go from there to C9H19OH, which is actually the same as C9H20O. So you don't need to draw this out, even though I just did, because I'm silly, apparently. Okay, you shouldn't have to do that, and you should still be able to work out how many hydrogens it's present in the molecule. I feel like I've done something wrong here. Let's see. Oh no, that's why. 20. Yes, don't do that. That's weird. Question 12. Which one of the following is not homologous series? Oh. Now, homologous series means that member differ by CH2. So that's all you need to do. Just see. That looks by... Oh, okay. Yeah, that B is the answer. You can't have two members with the same number of carbon and different number of hydrogen. That's an easy one. Number of structural isomers. Sorry about that. That is a weird laugh. Where's the cursor? I like this kind of question actually. Believe it or not. This is a good opportunity to revise how to use skeletal structure, which is probably the best way to indicate to work out how many isomers something have. It is the fastest method anyway. Alright, I'm gonna start with this. So 1, 2, 3, 4. Each of the end or the vertex represent a carbon. You don't show any hydrogen that's bonded to a carbon which in this case all the hydrogens, but you're going to show the chlorine. So the first proper possibility is to have the chlorine linked to the first carbon. 1, 2, 3, 4, and as you can tell, I have actually drawn one too many, so I need to delete them. Okay. The second case is having the chlorine here. So now that it is linked to the second carbon. Now, you actually cannot continue, because if I put, why do I keep doing that? If you put the chlorine here, you actually have to start counting from this end, which means that this molecule is identical to this one. So this is not another isomer. And if I put the chlorine on the terminal carbon here, it's going to be identical to the first one. So you only have two possibilities of having the chlorine being attached with 4 carbons as the longest chain. So what I tend to do now is I'm going to move on from the longest chain of 4 to a longest chain of 3. And obviously, if you have a longest chain of 3, the last carbon has to come from the middle as a branch. So you have a CH3 branch here. And I'm going to put the Cl side out here, so it can come out of the first carbon, or you can have both the Cl and the CH3 branch, that's not right, coming out of the second carbon. But I don't think there is any other possibility, because if you move the chlorine here, it's going to be identical to this one. So you have a total of 4 different isomers for this molecular formula. Structural isomers anyway. But naturally, no, I think you, oh yes, this thing has what is called a stereoisomers. You don't learn that yet. Moving on, question 14. Consider this reaction, and you need to work out the structure of Y. I think I got this question from like an old U12 exam. So congratulations, you can do some of them in theory. You need to recognize the type of reaction that is happening, and you need to do that. In order to do that, you need to recognize the type of molecules that are involving in these reactions. So the first one, you have an alkene. Alkene undergo addition. You should know that. And the product of addition is, well, it depends on what the alkene is reacted with. Now, in this case, it is reacted with H2O, so it's going to produce an alcohol in this case. So X is an alcohol. You need to know which alcohol though. So I'm going to draw X very quickly. I hope I have enough room. We'll see. CH3, CH3. So this one of these is going to break, and you're going to have a H being linked to one of them and an OH being linked to another. In this case, it doesn't matter which order is which, because you get an identical molecule regardless. So X, being an alcohol, is going to react with that. Now you need to also recognize that that is a carboxylic acid. And that's not how you spell carboxylic acid. It is an acid. I'm just going to write acid. And the product between an alcohol and a carboxylic acid is an ester. Alright, so I need to write an ester from this and that. Now this is not an easy question by any stretch of imagination. This is very, very difficult, because you need to spin the thing a little bit. This is what I was talking about with the cursor being there. I think it's too late for that though. Where I'm going to squeeze this in. Alright. Let's try that again, I guess. And it stopped working. Restart. Why does this do this to me so many times? What is wrong with my computer? Okay. Have we recovered? I think we have.